The first example of a random variable to which we'll apply the Chernoff method is the Gaussian random variable. So let's assume that x is a Gaussian random variable with mean 0 and variance sigma square. Let's compute the the moment generating function of x. So expected value of e raised to lambda x by definition is 1 over sigma square root 2 pi, and the integral of e raised to lambda x against the Gaussian density. So this evaluates to, so what one can do is in the exponent one can complete the square here to make it x minus lambda sigma square the whole square minus 1 by 2 sigma square into e raised to lambda square sigma square by 2 dx. This second term is a constant, doesn't depend on x, and comes out, and the rest of the expression is just the integral of the density of a Gaussian that is shifted, and so that integrates to 1. So we have that the moment generating function of a Gaussian is e raised to lambda square sigma square by 2. Okay, and this is for every lambda. So let's assume that there is t which is larger than the expected value of x, which is 0. So for all such t, we can compute cx star of t as the supremum, the unconstrained maximum over all lambda of lambda t minus sigma square lambda square by 2, which is cx of lambda. And this is a simple quadratic maximization of a quadratic, which finally gives you t square by 2 sigma square as an explicit closed form expression for the Kramer transform of Gaussian. Okay. So in fact, even if t is negative, you can apply the same argument to the random variable minus x and finally conclude that cx star of t is this basically a standard quadratic function given by t square by 2 sigma square. So the Chernoff bound here for a Gaussian reads probability that x larger than equal to t is less than equal to e raised to minus t square by 2 sigma square whenever t is greater than equal to 0. Okay, so you can think of this as a bound on the tail or the complementary cumulative distribution function of a Gaussian on the right side. With this, we'll go to our next example, which is that of a Poisson distributed random variable. So let's say that x is distributed as a Poisson random variable with the parameter v, which is the same as its mean. So in this case, the expected value, the moment generating function of x is expected value of e raised to lambda x, which is given by e raised to minus v, the sum of the possible values that a Poisson random variable can take, which is discrete values from 0 to infinity, e raised to lambda k, v raised to k by k factorial. Okay. Now one can evaluate this as follows. One can write this as e raised to minus v sum over k. Let's collect v into e raised to lambda k, v into e raised to lambda, and raise it to a common power k divided by k factorial. And what one can do is we can multiply and divide by the quantity e raised to v e raised to lambda, and then you have the sum over k v e raised to lambda raised to k by k factorial, and we have to divide by e raised to v e raised to lambda. And notice that by the definition of the Poisson probability mass function. This sum is equal to 1. It's just the sum of the Poisson PMF with the parameter v e raised to lambda instead of v. And so you get that the moment generating function is finally e raised to v into e raised to lambda minus 1, all of it in the exponent. So this means that the cumulant generating function of x is v times e raised to lambda minus 1. Okay, and in turn the Kramer transform Cx star of t is by definition the supremum over lambda greater than equal to 0 of lambda t minus Cx of lambda, which we just evaluated as v e raised to lambda minus v. So there's a plus v here. Okay. So if t is greater than equal to v, which is the mean of the Poisson random variable, then so let's try to just naively optimize this objective function, pretending that it's an unconstrained problem. So the natural thing to do is to take the derivative of the objective function and equate it to 0 and solve for lambda. So what you get when you do that is that t minus v e raised to lambda star is 0 at the optimum lambda star. So that just means that lambda star is equal to log t by v. Okay, and if t is larger than v, then log of t by v is a quantity larger than log 1, which is at least 0. So lambda star indeed turns out to be greater than equal to 0 if t is larger than equal to v. That is, the solution of the unconstrained maximum is the same as the solution of the constrained maximum. So one has that Cx star of t by explicit solution is nothing but t times the optimal lambda, which is log t by v, minus t plus v. And let's write this as, let's denote this as v times h of t by v minus 1 for reasons that we will see later. Okay, with h of x, the function h of x being defined to be 1 plus x log 1 plus x minus x, for defined for every x larger than equal to minus 1, so that the log is well defined. So you can see that this is Cx star of t is exactly v times h of t by v minus 1. Okay. So the Chernoff bound for a Poisson reads as follows. We have for all t greater than equal to v, probability x greater than equal to t is less than equal to e raised to minus v into e raised to minus t times log t by v minus 1. So as t becomes larger and larger, this bound essentially goes down as e raised to minus t log t. Okay. So this is roughly order wise. So this is order wise e raised to minus t log t. So you can think of it essentially as having an exponential type tail. Okay, slightly heavier than an exponent, slightly lighter than an exponential tail because of the presence of log t that multiplies the t in the exponent. A note here is that this bound is useful, okay, is practically useful naturally only when the right hand side, which is supposed to be a probability, is at most 1. Okay, so when the right hand side is strictly less than 1 is when it becomes useful. If the right hand side is larger than 1, anyway we know that the probability is has to be bounded by 1. So let's evaluate when, for what values of t this right hand side becomes starts becoming lesser than 1. This is the same as saying that t times log t by v minus t plus v is larger than 0, which in turn means that log t by v is larger than 1 minus v by t. Okay, so note that we've also assumed that t is larger than equal to v, which is the same as saying that t over v is at least 1. So let's think of t over v as some number x, this ratio x. If you plot this, let's try to plot on the x axis the quantity x. On the y axis, what we will do is we'll plot the quantity log x. We'll plot the difference between the left and right hand sides of this expression. So log x minus 1 minus 1 by x. And if you plot this function, it will look as follows. At 1 it will become 0, and it will rise only after some time. So before the rise comes the number 7, and after the rise comes the number 8. So at about 7.2 or something, this function again starts to rise above 0. So this is how log x minus 1 by x looks. And if we want this inequality to be useful, we know that we can only live with x to the right of this point of intersection with the x axis. So this roughly means that the bound is useful only if t is larger than, let's say, some number called 7.2 something, some fraction times v. Okay. So when you have t exceeding this number, this bound starts giving you something non-trivial. Another note here is that we don't need to be, we don't need to necessarily work with such a complicated form for the Kramer transform. We can also try to lower bound the Kramer transform Cx star of t to get looser but perhaps more insightful bounds. So one way of doing that for the Poisson distribution is as follows. We have that h of x, this function h of x that we wrote, to write down the Cx star of t here, okay, right here. This function, it's an easy exercise to show that this function has a nice lower bound given by x square divided by 2 times 1 plus x by 3, okay, all of this in the denominator. And so this means that for all t greater than equal to v, let me make some more space. So for all t greater than equal to v, Cx star of t, which was just h of t by v minus 1 into v, you can lower bound this as v by 2 into t by v minus 1 the whole square divided by 1 plus 1/3 of t by v minus 1. Okay. So we actually have a lower bound for Cx star of t, the Kramer transform in the exponent of the Chernoff bound, in terms of as a rational function. Okay, so as a ratio of two polynomials depending on t or t by v. So it's a quadratic form on the top, on the numerator, and a linear form on the denominator. So depending on whether t by v is close to 1 or not, you have either quadratic behavior for Cx star of t for large t, or for relatively smaller t, you basically have a linear type behavior. Okay. So this is what is called a Bennett or a Bernstein type tail inequality, tail bound. Okay, we'll see this in more detail later. Okay, this example was just to show that you can get non-trivial lower bounds for the Kramer transform of random variables. The third example is a Bernoulli random variable, which is probably one of the simplest random variables. So let's take x as being Bernoulli distributed with parameter p, and without loss of generality we will take p to be less than half, without too much loss of generality. So you can do the calculations to see that Cx, the log moment generating function of x, is simply log Pe lambda plus 1 minus p. And if one continues further, one can also calculate Cx star of t as 1 minus t log 1 minus t by 1 minus p plus t log t by p, which to some of you who have seen some amount of information theory or related areas is exactly what is called the binary relative entropy of t versus p for t lying between 0 and 1. Okay, so this is called the this is a very important object in information theory and statistics. It's called the binary relative entropy function. Or also the Kullback-Leibler divergence. Between Bernoulli distributions with parameters t and p. By the way, if t is larger than 1, then it's easy to show that Cx star of t is equal to infinity if t is larger than 1 or greater than t is larger than 1. Okay, so one can put an equal to sign here. And hence the Chernoff bound for a Bernoulli random variable with p less than half basically gives you that probability that x is larger than equal to t, less than equal to e raised to minus d t p for 0 less than t less than 1. Okay. The next application of the Chernoff bound will be for a sum of independent random variables. So think of a random variable z expressed as the sum of n independent random variables xi, x1 through xn. So if you start computing the cumulant generating function of z, so Cz of lambda just ends up being the sum of the individual cumulant generating functions of all the xi's evaluated at lambda. And moreover, now if all the xi's are also identically distributed in addition to being independent, then this Cz of lambda just becomes n times of each Cx of lambda, and consequently the Kramer transform Cz star of t just ends up being n times the Kramer transform of each random variable evaluated at t over n. Okay, this is just by algebra and using the definition of the Kramer transform. Therefore, we have the Chernoff bound probability that the sum exceeds t is less than equal to e raised to minus n times cx star of t by n, where x represents any of the xi's. So for instance, if you apply this to the sum of Bernoulli random variables, which is actually a binomial random variable with parameters n and p, where p is less than half, then what we get is that the probability that their sum exceeds t is bounded by e raised to minus n times the Kramer transform of a Bernoulli, which is d, the relative entropy, with parameter t over n relative to p. So in other words, if you normalize, so this is by the way for t larger than equal to the mean. Larger than equal to expected value xi, which is equal to np in this case. We have the following bound, and one can just divide by n throughout and reparameterize to get the following result. So the probability that the sample mean of n Bernoullis exceeds the true mean p plus a positive number theta is at most e raised to minus n d of p plus theta relative to p, okay, for I guess theta greater than 0. Okay, so you get this kind of tail inequality, and note that the nice thing here is that as n increases, the right hand side goes down exponentially with n, because d of p plus theta relative to p is just a constant, it doesn't depend on n. Moreover, there's an inequality called Pinsker's inequality, well known in information theory and convex analysis, that helps to lower bound the relative entropy by what is called the total variation distance, or the L1 norm. And in this case, this just means that d of p plus theta relative to p can be bounded below by 2 theta square, okay, irrespective of the p. So finally you have that the probability of the sample mean exceeding the true mean by an amount theta is at most e raised to minus 2n theta square, okay. So we'll see this later, but this is also what is called Hoeffding's inequality, or Chernoff-Hoeffding inequality. For Bernoulli random variables. Okay, so more later. The last example is going to be the derivation of the Chernoff bound for what is called a chi-square random variable. In simple terms, this is just the square of a Gaussian random variable. So think of squaring a Gaussian random variable, and that becomes one special type of chi-square random variable. So let's say that x is normally distributed, and you square x to get y. So the moment generating function of y will be 1 over sigma square root 2 pi integral of e raised to x square lambda x square, because that's lambda y, into e raised to minus x square by 2 sigma square dx. This is just equal to 1 over sigma root 2 pi integral e raised to minus x square by 2, collecting terms, 1 over sigma square minus 2 lambda dx outside. And you can convince yourself that if the exponent of the integrand turns out to be positive, then the answer is infinity. So this is when lambda exceeds 1 over 2 sigma square, and otherwise you can integrate this explicitly to get 1 over square root 1 minus 2 lambda sigma square otherwise. Okay, so if lambda is smaller than this critical value. So this means that Cy of lambda, which is Cx square of lambda, is equal to minus half log 1 minus 2 sigma square lambda for lambda less than 1 by 2 sigma square. So we will find it convenient to proceed with our derivation if we center y. Okay, so recall that y is x square, and let's center y. Okay, so just to paint a picture of how things look, y is x square. So if you plot the density of y, it will basically look something like this. And we know that the expected value of y, which is the expected value of x square, is sigma square. So this is just going to center y by sigma square. So let's center y and define z as y minus expected value of y, which is y minus sigma square, which is x square minus sigma square. So that z is a zero mean random variable. By centering a random variable, we will always mean subtracting its mean to get a zero mean random variable. So we have Cz of any lambda as a minus half log 1 minus 2 sigma square lambda, which is the cumulant generating function of lambda, and from that we have to just subtract lambda times sigma square, which is the mean of y. This holds for all lambda less than 1 by 2 sigma square as usual. So what about the main object of interest, which is the Kramer transform of the centered y, which is z? Okay, let's say assuming t is greater than equal to the right of expected value of z, which happens to be 0. Okay, so t is any positive number, and we'd like to compute Cz star of t to get an idea of the tail behavior or the Chernoff bound. So to do that, let's first start by writing Cz star of t. This is by definition the sup over lambda of half log 1 minus 2 sigma square lambda plus lambda sigma square plus t. This is by the definition of the Kramer transform. Let's call this as f lambda. We know that if t is greater than equal to the mean, you can always perform the unconstrained minimization. Okay, so lambda belonging to R. So how do we do that? We will differentiate f and set it to 0. So f prime at lambda star equal to 0 is equivalent to saying minus 2 sigma square by twice 1 minus 2 sigma square lambda plus sigma square plus t equal to 0. So you have a cancellation here, and finally what you will get is that lambda star, so this is really lambda star here, lambda star is just going to be 1 over 2 sigma square t over sigma square plus t. So substituting this value of lambda back, we get that Cz star of t equal to half log sigma square by sigma square plus t by sigma square for whenever t is greater than 0. So let's define this to be a new function, which is half of h1 of the quantity T by sigma square. So notice that the only thing that matters is the ratio of T over sigma square. Okay, so we have evaluated Cz star of T up to some reasonable level of clarity. So it's worth pausing to examine what we have done in a more pictorial sense. So recall that we have basically taken, so Z was essentially the centered version of Y, and so its PDF will look something like this: Fz of Z, okay, with mean 0. So we've essentially found the Chernoff bound essentially allows us to bound the tail probability of the random variables at going to the right of this number T. Now what about the left tail? Okay, how does the left tail look? What about if we wanted to investigate how this probability went? Okay, so in order to do that, we can one way to do that is to just invert to negate Z. So consider minus Z. Okay, so let's do that. So let's consider C minus Z. Okay, so likewise we can do similar computations for lambda greater than 0. If we start with minus Z, so C minus Z of lambda turns out to be minus half log 1 plus 2 sigma square lambda plus lambda sigma square, and C minus Z for the random variable minus Z, its Kramer transform turns out to be infinity if T is larger than sigma square, and it turns out to be this quantity half log sigma square by sigma square minus T by 2 sigma square if 0 is less than equal to T less than equal to sigma square. Now what's happening here? So it will be useful to draw a probability density function for the random variable minus Z. So on the x-axis if I plot Z, and on the y-axis if I plot f minus Z of Z. So what is minus Z? Minus Z is just, so let me extend this a little bit. Minus Z is having 0 mean and it's a negation of Z. Okay, so it's just going to be having a PDF that falls something like this. Okay, with this quantity being sigma square. Okay, because you have shifted Y by an amount sigma square to get Z. Okay, so its density is between minus infinity and sigma square. So which is the reason why if T is larger than sigma square, then the Kramer transform of minus Z is simply infinity, and it's otherwise finite. So let's denote this finite function by half h2 of T by sigma square. Okay, so we have essentially found the right tail decay and the left tail decay of a chi-square random variable, which is a Gaussian square. Okay, but the Kramer transforms are rather complicated functions. They are expressed as logarithms of rational functions of T and so on. So let's try to understand these functions, these Kramer transforms of Z and minus Z a little better by trying to lower bound them. And one way in which we can do this is as follows. So let's start with H1. Okay, so this is our first note. h1 of x, recall that it was minus log 1 plus x plus x. So this means that half h1x equal to minus half log 1 plus x plus x by 2. This is the same as minus log square root of 1 plus x by 2, and this can be lower bounded by 1 minus square root 1 plus x plus x by 2. This is because for any number alpha which is greater than 0, log alpha is less than equal to alpha minus 1 universally. So that's what gives rise to this bound. So using this, we get that the Kramer transform of z at t, which is the same as psi y minus sigma square star at t, which was earlier found to be half h1 t by sigma square, using this bound is at least 1 plus t by sigma square minus square root of 1 plus t by sigma square. Okay, so this is what is the right tail bound, the right side tail bound for y or for x square really. Okay, which gives you basically some insight about how this bound looks as a function of t. Okay, so it's essentially a linear function in t minus the square root of 1 plus t, 1 plus constant times t. On the other hand, the left side tail of x square, which is really the right hand side tail of minus x square or minus z, can be bounded in the following way. So the second point here is that h2 of x, which is minus log 1 minus x, one can easily show by an exercise that this is greater than equal to x square by 2 for all non-negative x. Okay, this is basically because log 1 minus x, if you think of its Taylor expansion, this is basically minus x square by 2 minus x cube by 3 minus so on. And since you are subtracting off, this is at most minus x square by 2. Okay, and that's basically the inequality above. Okay, in spirit. So what this finally gives us is that the left tail of z, which is really the right tail of minus z for any t greater than equal to 0, which is just half h2 t by sigma square, is lower bounded by t square by 4 sigma square, just a quadratic function. Okay, so this is the left tail of x square. Okay, centered suitably. So if we compare the left and right tails, the tail decay, the exponential tail decay suggested by the Chernoff bound, what we find is that the right side tail essentially decays as e raised to minus constant times t, e raised to minus t, like an exponential, whereas the left tail decays as e raised to minus x square, okay, e raised to minus t square. So the right tail is much more heavier than the left tail. Okay, so this is to be expected because the left tail is really bounded; it doesn't go beyond a certain value. So we'll probably discuss more of this when we come to sub-Gaussian random variables and variables that are heavier than sub-Gaussian. That concludes this lecture. Thank you.